We calculate process capability by checking how well our process curve fits within our specification boundaries. But what if you only have one specification boundary or a unilateral tolerance? That's what we'll be discussing in this video, and we'll also get a nice example of the E number, often used in Europe. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today's video actually springs forth from a question by one of you viewers, and he asked, how do you do a CPK when you have a unilateral tolerance? And at first I thought, well, it's quite simple. Didn't really give too much thought about it because, as you will see, you just drop one of the limits and basically you're done with it. So the statistics, the mathematics, they are really simple. But many cases where you have only one tolerance limit, many other things than just CPK optimization come into play. And that is what makes this question an interesting one to discuss. So let's do that today. Now, first off, when we do CPK, we have the spread of our process. We usually take 3 standard deviations and then check how far that is from our upper or lower specification limit. And then what you do with the CPK is you take the minimum of these two, and because generally we would like a higher CPK, what we will do in practice is we center this process. But sometimes for a process only one of these specifications is really important. For instance, if you have a weight, then there is a minimum weight that really needs to be in your package, but if you go over, well, that's basically your problem as a producer, but does not harm your consumer, is not a problem according to the specifications. And in this case, there is no upper limit, so your CPK will always be with this minimum limit. So you check how many standard deviations is your process away from this minimum limit. But before we get into how high would we like our CPK, it's very important to check for normality. We should always do this when we do statistics based on normal distributions, and almost all of the standard deviation type of distributions and statistics, they do use it, so we should check it, but specifically in cases where you have a one-sided tolerance, and also if there is one absolute minimum, a value cannot be less than 0 for certain parameters. You can only get to a certain value above. What you will often see is that your data is not normally distributed, but is highly skewed, for instance. And in these cases, we cannot simply use CPK or control charts. So be very aware of that. I think we should spend a completely different video on that part, but suffice to say, when you have only unilateral tolerance, be doubly aware of normality checks. Now then, the thing I already said, how far do we need to be away from the limit? So how high of a CPK do we want in our process? If we have a double specified product, so we have a range, well, we know that the CPK will be highest when we dead center our process. But if we have only one limit, then the easiest way to improve our CPK is just to move the mean, and the CPK will go up, but your costs as well. And that's why we have to check, especially with unilateral tolerances, what does our customer demand from us, or maybe what do we decide is a good level. So that one will be a very important one, and after that we go into cost. And these two will often be linked unless a customer or rules and regulations stipulate exactly what CPK you need. Now, what we often see in especially steel industry parts, things like that, is that customers are very used to putting a CPK demand. I want these widgets and I need you to produce them with a CPK of 1.67 minimum. Then you get a very clear CPK demand. But in other industries, and also especially in the food industry, it's not very common to ask for a CPK. In fact, it is very common to ask for minimum levels. And then how do you decide what does a customer still accept? And there is one very interesting case, which is not so much a customer, but more of a rules and regulations thing, and that is the E number. for estimated weight, estimated volume under European law. And at first glance, it feels like a basic unilateral tolerance, but this system actually gives you a lot of information for us as process engineers to understand how capable our process should be. Now, for those unfamiliar with this E number, it is used in pre-packaged products with a fixed weight, and it stands for the estimated weight. And basically, it is a law governing how much should be in the smallest packages to still fit into this rule, and the center should be at least as high as what you indicate. So with an example here, let's say we have a 1000 milliliter can of milk, and for 1000 we know that the norm is that you are allowed to deviate by 15 milliliters or a maximum of 30. This one is always double, and what that means is that on average your entire batch should be at least 1000 milliliter per product. So that's the average, but a batch can be quite big. Now, if they take a sample, what you can have is, of course, since it is an average, a couple of cartons can be a bit less, a couple of cartons can be a bit more. But then comes in this minus 15 milliliters. Only 5% of your product is allowed to be less than 15 milliliters under the 1000. And none of your products is allowed to be more than 30 milliliters underweight. So if we have a not too capable process, what we would have is something like that, where our mean is at least above the 1000 that we offer, and here we have no more than 5%. And basically what you will see a lot in industry is that we have the check weighers, and as soon as this gets over our 5%, we start to shift the process up and dump out some of the cartons to make sure we fit into this model. But as Six Sigma engineers, we would of course like to reduce the variation and make this a more capable process. And here especially, we can use all of this information to calculate what sigma level, or actually what standard deviation, do we need to be optimal here. To what point will improving our process capability still give us money, and from what point is it not that useful anymore. And basically what we want to go to is something that looks like that. So we are, well, dead centered, and this is still only 5%. Now, this curve we can calculate, and if you just take this distribution, you know that only 5% is allowed to be more than 15 milliliters off. What we see is that here we need a sigma level, well, a standard deviation of 9.1. If we have a standard deviation of 9.1, then we will have exactly 5% over 15. It will mean, by the way, that there will be 0.05% under this minus 30. So we should be even a little bit closer, but we'll get to that in a bit. But basically, this on first glance would be our ideal factory. Now, what I already promised, it's not the end of the story. Within Six Sigma, we often talk about the 1.5 Z shift. So what we basically mean is when we put up control charts, we will probably not see a shift in the centering of our process until the process has shifted at least by 1.5 standard deviations. So this we need to take into account. When we see it, we can probably still correct the rest of our batch, so we will be able to get back to our promised 1000 milliliters on average over the whole batch, but we will have already produced a whole number of packages here. So we need to determine that standard deviation, where if we shift 1.5 standard deviations and then we take our curves, we still get only 5% lower than our minus 15. Now, there is not a direct calculation to do. Well, there probably is somewhere, but the easiest way to do this is just to solve for it in Excel or to iterate it a little bit yourself. But what you get when you do this is the picture will be relatively clear. We will be 1.5 sigmas to the left, and still this is only 5%. And we get that with a sigma of 4.8. Now, that basically tells us, of course, we are not allowed to produce the whole batch to the left here. Remember, the whole batch should always still be centered, but this allows us a half hour in our shift to produce a little bit less before our systems see it and we correct everything to have a higher weight again. But this basically gives us our answer to if we have only a unilateral tolerance, because the weight is only unilateral, and our customers, in this case the law, gave us sort of a description how much deviation they will tolerate, we basically can make our own CPK demand. And maybe this is not per se a CPK demand, but the answer for our production is in the end the same. What standard deviation should we aim for? And as long as we are above this standard deviation, it will generate money if we can improve the process. As soon as we are here, just purely focus on control and don't try to improve it further, because it will not help us anyway and it will be a waste of our effort. So to rehash, when you have a unilateral tolerance, the basic CPK calculations are very easy. You already determine upfront which side you are going to test, but the practical situation around when you have a one-sided limit, they become very interesting because it becomes more of a cost and what is our expected quality level picture. It's a different question where we will have to use information that our laws or customer provide. Maybe they provide a direct CPK, but more often they will tell it to us in slightly different ways that we have to recalculate back into what level of standard deviation do I need, when is my process capable. And in many situations where you have a one-sided tolerance or a tolerance that has basically two sides, but one side is favored by the customer, there's almost always a bigger problem with normality than when you have a normal process just running with its natural variation. Now I hope that this clarified how to use CPK when you have unilateral tolerances, and also that this example got you thinking a bit about ways that we can translate customer demands that are not always in CPK or specifically our process metrics into a metric that we can use, because this actually is very translatable when you check the percentages that they demand. And if you like that, don't forget to tell me hitting that like button. Also subscribe to my channel if you haven't done so already. And please drop me a comment telling me what part of CPK implementation still really is a question to you. Where would you like to have some feedback from me, the rest of the community, and how to put this CPK into process, into action. And for now, I wish you the best of luck with your process control, and as always, enjoy your continuous improvement journey.